Hello everyone. The purpose of this recording is to showcase microservices-based architecture in combination with the tools provided by Netflix open source software. The business use case used to demonstrate this is an order management system. Order management systems are the most widely used applications, typically consisting of flows that take care of order processing, purchasing, invoice management, warehouse management, marketing, accounting, and much more. A system of this nature needs a mature design approach that should integrate with existing systems into a single unified system. Keeping this in mind, we have explored the tools provided by NetflixOSS to determine if these would be beneficial for seamless integration with existing systems. This demo limits the scope to a simple workflow that begins with the user placing an order for a certain quantity of a product. If the product is available as per the quantity requested, an invoice for it is generated, payment is processed, and the order is set to be fulfilled. The order can also be unfulfilled in case of certain error conditions. In such cases, the reasons for its unfulfillment are captured. The flowchart shown is the representation of the workflow implemented in this demo. When an order is placed, it will go over various states. It is considered as complete when its state is shipped. If the products requested by an order are not in stock in the inventory, or if the payment is incomplete, then the order goes to cancel state. Also, if the invoice or the payment functionality is unavailable, then the order state is aborted. Shown next is a representation of the workflow when we apply microservices-based architecture. Microservice software architecture allows a system to be divided into a number of smaller, individual, and independent services. Each service is flexible, robust, composable, and complete. They run as autonomous processes and communicate with one another through APIs. Each microservice can be implemented in a different programming language on a different platform. As we see here, the dotted line boxes, namely the order service, the inventory service, the payment service, are all microservices. Each of these services have an independent responsibility. For instance, order service is used to create and place an order for products. Inventory service checks the availability of the given product in the inventory. The invoice service generates an invoice for an order. The payment service processes the payment, and so on. Now let us consider a few points while implementing microservices. Point number 1, service discovery mechanism. For a client to make a request to a microservice, it needs to use a service discovery mechanism. A key part of service discovery is a service registry. The service registry is a database of available service instances. Point number 2, features such as security, caching, request routing, and monitoring are to be handled. Point number 3, scaling. Microservice instances based on the load or the demand should get added or removed. Point number 4, appropriate error handling or fallback mechanism in case of unavailability of a service. Point number 5, packaging and deployment of microservices. To take care of these points, we make use of tools provided by NetflixOSS. As mentioned, a client needs a service discovery mechanism. This is provided through the Netflix component Eureka Service Registry. The Eureka server is responsible for managing a registry of service instances, determining the location of service instances to send requests. It also provides a means to register, deregister, and query instances with the registry. Hence, the microservice, order service, inventory service, product service, invoice service, payment service are all registered with the Eureka registry. Apart from registration of service instances, the microservices also need to be discoverable. For this, they need to be Eureka client enabled. Once discoverable, one microservice can invoke the services of another microservice. For instance, now order service will be able to invoke the services of inventory service or invoice service. As mentioned earlier, when implementing microservices, request routing, monitoring, caching also need to be taken into account. For this purpose, Netflix provides something known as a Zool proxy. Zool acts as an API gateway or an edge service. It is a front door for all the requests from devices and websites to the backend. Some of the features that Zool provides are: it supports dynamic routing so that it allows rapid change in behavior in case of production issues. It authenticates and rejects requests that do not fulfill the authentication requirements. It provides insights and monitoring for accurate view of production by implementing something known as filters. Ribbon is used for routing requests as well as software load balancing. It is a part of the Zool proxy component. The proxy internally uses Ribbon to locate the service instance to forward to via discovery. When multiple instances of the same services run, Ribbon manages the load balancing by delegating the request to the running instances in a round-robin fashion. Since all our microservices are up and running, what we can do right now is to place an order for the product. What we see here is a dashboard, the Eureka dashboard, which shows us all the services that are currently registered with Eureka. We have the customer service, the inventory service, the invoice service, order service. These are all the services that are currently up and running with Eureka. Each of these services run on different ports. Product-service, payment-service, order-service, these are nothing but the service IDs of the services. Now what we can do is place an order. Here we'll be firing a REST request to place an order. The request has the ID of the customer who's placing the order for a product with ID 1 and quantity 1. The cost of the product is $250 and the amount paid by the customer is $250. The payment type is debit. Now, if we were to quickly take a look at the database, what we have is the products table that mentions that product ID 1 represents Motorola X-Play. It's a mobile phone, and product ID 2 represents a Lenovo laptop. So what we are trying to do is we are trying to place an order for product ID 1, which is Motorola X-Play, for 1 quantity. It's a very simple workflow. So let us send a request. So what we essentially have is an order with ID 1 for the product ID 1, and the order is fulfilled and hence it is shipped. Let us quickly take a look at the entry that is made in the orders table. So as we see here, this is the entry for product ID 1. This is the payment ID that has been generated. This is the order amount, the quantity, and we have the remarks that mention that the order for the product ID 1 has been shipped. Note that each of these microservices, the order service, payment service, invoice service, are deployed on a Docker container. What we will do is we'll be accessing the Portainer utility to take a look at the logs that are generated. So let us take a look at the order service and the logs generated in order service. The order service is the entry point service which will in turn internally invoke the various other services, starting with the inventory service. So as we see here, first the order with ID 1 is created. It then invokes the inventory service to check for the availability of the product and for the specified quantity. Once inventory service confirms that the quantity is available, it next goes to the invoice service, which is responsible for generating the invoice. It initiates the payment for this particular order. It checks if the payment that is made for the order is complete, that is the order amount and the amount paid by the user match. Once that matches, it will update the inventory. That is, it will deduct the number of quantities for which the order has been placed. Once the inventory is updated, the order is shipped. It is ready for delivery. So this is the sequence of calls. So behind the scenes, we have at least 4 to 5 microservices that get invoked, with order service being the starting service. Now, if we were to make a payment that is lower than the cost of the product, let us see what happens. So let us just pay 200 for a product that actually costs 250. Maybe this time the payment type is Visa. Let me just run. So as you see here, the order cannot be processed because the payment is incomplete. If we quickly take a look at the orders table, we will see that the status of the order is cancelled. The message mentions that the order could not be processed because of incomplete payment. Similarly, if we were to place an order for a very large quantity, in such a case also the order is not processed because of insufficient stock in the inventory. Let us just refresh our table. And there we go. We have the order in the cancel state, and it could not be processed because of the insufficient stock in the inventory. So what happens behind the scenes is that each of these services, so if the payment is incomplete, then the payment service, or if the stock is not sufficient in the inventory, which means the inventory service, each of these service throws an exception, and that exception is handled by the order service because of the fallback mechanism that is supported. We'll talk about the fallback mechanism a bit later in this demo. But essentially what it does is the fallback mechanism takes care of handling this particular exception, and what we have is a user-friendly message that indicates the reason for the failure. Now, as we know that in a distributed environment, inevitably, some of the many service dependencies will fail. Say, for example, the payment service is down or unavailable. In such a scenario, Netflix provides a tool called as Hystrix that isolates the failing services and hence prevents cascading effect of failures. Hystrix also provides fallback options that improves the system's overall resilience and fault tolerance. So when the payment service is down, a fallback method is triggered that informs the user about the service unavailability without causing a ripple effect to the system. If an order is placed when these services are down, the fallback ensures that the order is marked as aborted in the database along with the comments mentioning the reason. Let us take a look at such a scenario. In order to do that, the first thing that we'll have to do is to bring the service down. So what we have is a Jenkins job in which we can select the service whose instance we would like to make 0, which means that the service is pulled down. So once we mark it as 0, we will see that the payment service is no longer available. So here we go, the payment service has been pulled down. We can just confirm this by refreshing the dashboard. Yeah, here we go. So we no longer see the payment service in the list of instances that are currently registered with Eureka. Now that the payment service is down, we will try to place the order again. Let us give some valid quantities. So let us say we are trying to place an order for the product ID 2, which represents a laptop, for let's say 5 quantities, and then the order amount totally say comes to about $15,000, and the user is paying the same amount. The payment type is Visa. Now let us try and place this order. There we go. So what we see is the order could not be processed because of service unavailability. It's a user-friendly message that indicates that the service is unavailable and the user will have to try placing the order again in some time. Let us quickly take a look at the logs that are generated in Portainer. Right. So here we go. This was the order that got created. It checks the inventory for the availability of the product, which means that it hits the inventory service. Inventory service returns that the product is available. It goes to the invoice service. Invoice service in turn initiates or triggers the payment service. And what we have is a situation where the payment service is down. So we have the circuit breaker that gets enabled. We immediately see that since the payment service is unavailable, the flow needs to be terminated, but the system did not come down. So it is efficiently terminated with a user-friendly message, and this can be also viewed in the database. So we have the order that gets aborted because the payment service was unavailable. For real-time monitoring of the service performances, we also have something known as the Hystrix dashboard. What we can do is, let us trigger this request again and take a look at the payment service and the Hystrix dashboard, how the Hystrix dashboard behaves. So as we see, these are the services that are being monitored real time by Hystrix. We have the make payment, check inventory, the check payment complete, and the save order services currently. Let me fire the request again. The service is still down, and here you go. Here we see that the make payment service, there is one in red, which means that there has been one failure. So real-time monitoring can be done with the help of Hystrix. So to summarize, we use Hystrix Service Registry and Client for service registration and discovery. Zool is used as an API gateway for typical features like routing, monitoring, runtime filter changes. All the logs that are currently getting generated in Portainer are generated because of the post filters that have been created behind the scenes. So this is actually Zool that is in action. Ribbon is used as a load balancer. So currently we just had single instances of all the services that were running, but it is very much possible for us to have multiple instances of the same service to run. Like for example, order service, we could have 5 more instances if the number of order requests are high in number. So if there are multiple instances of order service, then we will have ribbon that will balance the load. It will route the requests in a round robin fashion between all the 5 instances of order services. Then we have Hystrix that enables resilience by supporting fallback mechanism. We also have the Hystrix dashboard, which helps us in real-time monitoring of these services. So as a conclusion, Netflix tools, when used in tandem with the microservices architecture, can offer advantages from independent scalability of diverse application components to faster, easier software development and maintenance. Thank you.